Okay, now let's go in more depth for the expandable casting and processes. So the first technology we're going to cover here is going to be the sand casting, which is one of the most widely used in the casting and processes. The nearly all the alloys can be sand casting because the sand pattern, or sorry, the sand mold can take as high a temperature as possible. So can cast metal with high melting temperatures like the superalloys or the titanium. Casting range in the size from the small to a very large. Small can be anything like the spanner. The large can be anything like the engine for the ship, engine block for the ship. Production quantities, once again, can be vary from one part to millions. The sand casting process steps can be presented in this flowchart. So start with the core making. Pattern making is going to be the first one. We're going to prepare the sand, mold making, add the core if needed. Okay, raw materials preparation, melting of the raw materials, and pour it in the mold cavity, solidification and the cooling, removal of the sand mold, cleaning and inspection, and we're going to have the finished casting. Okay, that's straightforward. Once again, that's the flow chart of the sand casting processes. Now let's have a look for the steps as a photos. So we prepare the sand, we prepare the box, and we had the pattern inside. So put the pattern at the piece of wood, and we're going to put the flask. We're going to fill it with the sand. We compact it. Then we're going to flip it to the other side. Now we clean the surface. We put some talc powder. We prepare the channel for the pro. Okay, we put the pie for the pro, and we add the top layer. Add more sand. Compact it. Open the pro channel. Remove it. We're going to have a clean surface. Open the tool house, the crop and drag. Remove the pattern. Now we have a cavity, as you can see here. We cut the runner. We cut the runner in this step. Close the crop and drag. Add the pouring metal. Leave it to solidify. Open the box. Take them out. That will be the initial shape with the pro and the razor, and then we can cut them out to have the handles. Very simple steps. Now let's go to the pouring process. I hope this is a video. No, it's not a video. Okay, anyway, that's a flow simulation. You can see we can add the material. It's going to fill the cavities. It's going to have the vents to avoid having the blocking due to the pressure. You can see that the razor is going to be solidified after the solidification of all the parts. That's mainly to keep some liquid metal to compensate the shrinkage in the cassette part. So this is the cassette part. As you can see, this will be the the runner, the razor, and this part will be cutted, and this part will be the cassette part. This can be remelt and reused. That's another example for making the angle pipe. So what are the patterns? Patterns in the sand casting are going to be used to form the mold cavity. And it is a full-size model of the original part with even oversized. Now why oversized? Because we said that the shrinkage will cause the casted part to be shrink, and thus we need to compensate the shrinking by this method. One primary requirement is that the pattern and therefore the mold cavity must be oversized, first to account to the shrinkage in the cooling and the solidification. Second, to provide enough metal for the subsequent machining operations, like we're going to remove the materials to get the diameter, for example, to 20 millimeters, I need to have the casted part to be at least 22 or 23 millimeters, so I can remove this millimeter by the machining processes. This is just an example for the dimensions. So you can see that the pattern can be a solid pattern. It can be the split pattern with two halves. It can be the match plate pattern. We can have the cope and drag pattern, so you don't have to get the same block as in two boxes and use them together. You can make the cavity of the drag and the drop individually, then you can close them together, and this can be used for the process of the high production. The pattern materials can be wood, can be metal, and can be the plastic. The wood, if I can use it for one time, and because the sand itself is going to be wet, so usually we are going to use the varnish on the top of it to give it some protection from the humidity. Otherwise, we can make the metal one, which is going to be heavier, of course, and it's going to last longer. But the problem is that the cost is going to be higher. We can have the plastic one, which can have the property in between the wood and the metal. If I would like to have a cavity within the casted part, I have to use the core, and the cores serve to produce an internal cavities and holes in the casting in some cases. They have to be supported by the chaplets. This is the chaplets. For more stable positioning while we pour the metal. So it's going to be supported by chaplets. We're going to run the molten metal to fill the cavities around it, then solidify, and we're going to have the tools internally in the part like what we can see here. The cores are made of the foundry sand with the addition of some of the resin to strength by the means of the core boxes. So we're going to get the sand. We're going to put some resin on it. We're going to put it in the box of the making of the core itself. Then we can bake it, so it's going to be very strong. Okay, this example of the two cores halves was ready for baking and complete the core made by the gluing of the two halves together to have it as one part. So once again, these are the examples to make the core. No, actually, this is not the core. These are the cores, and we have one in the lab that we're going to show you. Now, the foundry sand itself. The silica, which is the sand that you can find on the beach, or the silica mixed with the other minerals is going to be used. Good refractory properties for the high temperatures. Small grain size is for the better surface finishing on the pot, while larger grains are going to be more permeable, allowing for the gases to escape during the pouring. Okay, now just let me explain these two parts. If I'm going to have small grains, the cavity between the particles of the sand is going to be too small, and this will trap the gas within, and this is not going to be a good thing for allowing for the air inside the cavity to escape. Irregular grain shapes strengthen the mold due to the interlocking between the parts compared to the round grains. The round grains is not going to be holding each other, so the possibility of having the mold to be collapsed is going to be quite high. While if I'm going to have irregular grains, when I'm going to compact them, they're going to holding each other by the interlocking. Disadvantage for the irregular grains is that going to be the interlocking reduce the permeability, which is the, as we said once again, the capability for the gases to escape. Binders used with the foundry sands are, the typical foundry sands is going to be a mixture of the fresh and recycled sand, which contain definitely 90% of the silica, 3% water, and 7% the clay, to work as a binder between the particles. So once again, the grain size and the grain shape are going to be very important as they define the surface quality of the casting and the major mold parameters such as the strength and the permeability. Okay, so you can see that the bigger the particles are, the bad surface roughness we're going to achieve. The interlocking will prevent the permeability for the particles. Types of the sand molds we can have. The first type is called the green sand mold. mixture of the sand, clay, and water. The name green coming because it's wet. The dry sand mold, organic binder is going to be used rather than the clay. We have the skin dried mold, where the drying mold cavity surface of a green sand mold to a depth of 10 to 25 millimeters using the torch of heating lamps. The mixing of the foundry sand can be done in multiple steps. This will be the step number 1. We're going to have a continuous type, the one on the left, or we can have the patch type to the right of the sand Mueller. The blow blades move the sand and the Mueller wheels mix the components. The mold making, where the sand compacting can be done by hand or by means of the machines. So we have the hand packing, like the one we saw in the series of video photos before. We can have the machine packing, and we can have the automated methods. Desirable mold properties gonna be, first, we have a good strength to maintain the shape and the resist to erosion. With the permeability, as we mentioned once again, to allow for the hot air and gases to pass through the voids in the sand. The thermal property, thermal stability to resist the cracking on the contact with the molten metals. We have the collapsibility, where the ability to give away and allow the casting to shrink without cracking the casting. The reusability, where the sand from the broken mold can be reused to make the other molds. There is a term which is called the vacuum molding. It's considered to be a quite new technology if we consider the long length of the casting processes, which is something like just 30 or 40 years old in this case. So you can see that we are going to have the film heater, we're going to have the EVA film, we are going to put the sand in the box, okay, the pattern, the part, well, actually start the form here, just give me 1 second. Okay, vacuum molding is going to be advanced sand casting method. The vacuum pressure effects is going to be added to make the sand mold rather than the using of the chemical binders. Then the whole sand will be reusable. So once again, we put the pattern, we put that in a box. We are going to fill with the, we're going to actually fill the suction box here with the sand, do the suction. So the formed film here is going to make the sand at the lower level to be compact and high. We're going to do the same thing with the top one, just do the suction. So the particle, the sand will be held due to the negative pressure. Simply remove the pattern, have the 2 halves of the mold closed, fill the molten metal, and then we're going to have the casting part. Simply by stopping the suction, the whole mold will be collapsed, and thus we are going to be able to use the sand once again. It's going to be very clean and very easy to be used. The problem with that is that the time required to prepare the mold is going to be even longer than the normal molds we have. So the advantages are easy to recovery of the sand since no binders. The sand does not require a mechanical reconditioning done when the binders are going to be used. Since no water is going to be mixed with the sand, the moisture-related defects are going to be avoided. Disadvantage is slow processes and not readily adaptable for mechanizations. We have the shell molding. Now, another technology, quite advanced, gives you a good surface finishing. Also known as the DBM process, or the ceramic shell molding process, because the mold is going to be a thin wall shell of the ceramic or the sand. It's called the shell mold. So now the pattern is going to be made from steel. We're going to have a sand with resin binders. That will be step number 1. Since the solid naphthalene is going to be used for preparing the molds, a complicated shapes and thin casting can be produced with this process. So once again, we're heating the pattern. This is a sand with resin binder in the dump box. We're going to flip the box. So the contact area between the hot pattern and the sand will simply begin to build up a layer, thin layer of the shell. Now we'll flip it back. We have the shell built up. We are going to put it in the oven to give it enough strength. Remove the shell. Support it in the flask. Put the metal short around it. The clamp, of course, to hold the two parts together. And now we have a cavity. This cavity is a mold cavity. So fill it with the molten metal, leave it to solidify, open it, break the shell, and you're going to have the part ready for you. Once again, this is an example for the part. So this is how the shell looks like. This is your core inside, and you can use it to make the cylinder head. These are even more example for the part. This is the pattern. This is an example for the product. That's what we have in the foundry. You can see that we can have it as a mass production because mainly we can make as many as we can of these shells together. These are in the flask. We just need to support it with sand or the metal pips, and then it's going to be work. So we said it's going to give you a good surface finishing, good dimensional accuracy, suitable for the mass production, but it's expensive metal pattern. That's its disadvantage. Area of the application is the mass production of the steel casting, which has less than 10 kilograms in mass. Maybe this can be an example for one of the products. Now the other type is the loose form. And in this technology, the pattern is going to be made of foam. Loose form, also known as loose pattern process, evaporative foam process, full mold process, and expandable polystyrene process. Multiple names for the same technology. The mold is made from sand packed around the pattern made of the polystyrene foam. The foam pattern is going to be evaporated when we are going to add the molten metal. The polystyrene foam pattern includes the sprue, the razor, the gating system, and the internal cores if needed. The mold does not have to be opened into a cup and drag sections because it's going to be just sand with cavity inside. This cavity is actually filled with the foam. The foam will be evaporated when we get to add the molten metal. So these are examples of the patterns made of foam. For a complicated shape, you can see it's going to be consist of multiple parts that's going to be glued together. Different shapes, different patterns, different products can be made with this technology. Okay, so this will be the end of, no, we still have more to go. Yep, so this guy actually gluing the pattern parts together. He putting the part into a slurry ceramic to have a shield around it. The advantages are, first, the pattern need not to be removed from the mold later. This will make the process much faster. Simplified, and it speeds the mold making because the two mold halves are not going to be required as in the conventional green sand mold. But this advantage is a new pattern needed for every casting, and also the economic justification of the process is highly dependent on the cost of the producing of the pattern itself. Let's see what application we have for this technology. First, the massive production of the casting of the automobile engines. We saw one of those earlier, right? They mold the polyester foam patterns and then feed them into the downstream casting operation. Another technology is the investment casting, or known as loss wash process. In the investment casting, the pattern is going to be made of wax, which is going to be melted after making the mold to produce the mold cavity. So we make the wax pattern. It can be made by hand, or it can be done by having a mold for the part. And once again, the pattern can consist of multiple parts that will be simply glued to each other to make a bigger pattern or more complicated pattern. We glue them on the wax sprue. We soak it and dip it in the refractory ceramic, and we're going to have a shell to be built up around the tree and the particles. Heating up the shell, the wax will be melted and this can be reused later. Support the shell with a sand in the flask, pour the molten metal in, and you're going to have the parts inside. Breaking up the shell, you will get the parts ready. Take them out of the tree, and this will be the individual product. So this is making all the pattern. That's an example of different types of the pattern. That's how we going to dip it in the ceramic. Okay, so the area of the applications are: first, small in size, complex parts such as the art pieces, jewelry, dental fixtures from all the types of metals can be made. Used to produce machine elements such as the gas turbine plates, the pinion gears, and extra, which do not require or require only a little subsequent machining later. So once again, these are the example. That's the pattern to be dipped in the ceramic. That's the casting process. These are the products which can be made. Okay, that's an example on how to make the pump body by using this technology. The advantages are: first, the parts are going to be great complexity and the entry chassis can be casted. Close dimensional control and good service finishing. The wax can usually be recovered for reuse, and this is a net shape process. Additional machining not normally going to be required. The disadvantages are many processing steps are going to be required and relatively expensive process. The other technology is the plaster mold casting. So instead of the ceramic, we're going to make the plaster to make the things, or the gypsum. So similar to the sand casting, it's said that the mold is going to be made of the plaster or the Paris, or we know it as the gypsum. In the mold making, the plaster and the water mixture is going to be poured over the plastic or the metal pattern and allows to set. The plaster mixture is going to be readily flows around the pattern, capturing its fine details and good surface finishing. Advantages are good accuracy and surface finishing, and the capability to make ethnic cross sections. But the disadvantages are the mold must be baked to remove the moisture from it. Also, the moisture can cause a problem in the casting, as you know. The mold strength is going to be lost if it's going to be over-baked, because gypsum is going to lose its strength if it's going to be exposed to a high temperature. The plaster molds cannot stand high temperatures, and this will limiting the process to a lower melting point alloys. To overcome this problem, we have the ceramic mold casting, because you know the ceramic can withstand higher temperature. Similar to the plaster mold casting, except that the mold is going to be made of refractory ceramic material that can withstand the higher temperatures than the plaster itself. This can be used to cast steel, cast iron, and other high temperature alloys. The applications are similar to those of the plaster mold casting except for the metal cast used. Advantages are good accuracy and finishing, which is also similar to the one we have in the case of the gypsum mold. So that's it for the expandable mold casting, and we're going to go to the permanent mold casting in the part number 5.